Hello, first year students. Today we're going to discuss about lesson 5, which is all about matter. And you know that matter is essentially anything that occupies space and has mass. So in this lesson, we will explore the four phases of matter and learn how to distinguish and describe each one. We will also delve into the differences between physical and chemical changes and how these changes impact the properties of matter. Furthermore, we will compare and contrast physical properties and chemical properties and discuss how these intensive and extensive physical properties can be observed and identified. By the end of this lesson, we are expected to distinguish and describe the four phases of matter, distinguish between physical change and chemical change, compare and contrast between physical properties and chemical properties, and lastly, discuss how intensive and extensive physical properties can be observed and identified. Now, without further ado, let us start. So, what is matter? Matter is essentially everything that we can touch, see, smell, taste, and experience. It's what makes up the world around us. So, in scientific terms, we can say that matter is anything that occupies space and has mass. It can exist in many forms, and we can commonly divide it into different phases, such as solid, liquid, gas, and plasma. So we're probably familiar with these terms, but let us describe and define them anyway. In a solid, particles are closely packed together in a fixed shape. So let's think of a rock or a piece of wood. These are examples of solids. Now, in a liquid, particles are slightly more spread out compared to a solid, and liquids can take the shape of their container. For example, water and oil are examples of liquids. Now, in a gas particles are widely spread out and fill their container. The air we breathe is an example of gas. Plasma is a bit less common in our daily lives, but it's still very important. Plasma is actually an ionized gas with free electrons. Examples of plasma include lightning and the stuff inside neon lights or neon signs. So, by understanding these different states of matter, we can start to understand the world around us on a much deeper level. So, we can begin to see why certain materials behave the way they do and how we can manipulate them to serve our needs. Now, let's talk about solids. We know that when we hold an ice cube, it stays in its ice cube shape and doesn't just start flowing through our fingers like water would, right? So that's because ice cubes are solids. And solids have a fixed shape and volume. This means they don't change their shape or size unless we do something to them, like cutting them or melting them. Now, let us all imagine the tiny particles that make up that ice cube. In a solid, these particles are super close together. They are practically hugging. But unlike us, they can't move around. They can only vibrate in place. This is why solids are rigid and they can't flow like liquids or gases. And you know what else is a cool fact about solids? They can't be easily compressed. This means you can't really make a solid object get smaller by applying pressure. Now, let us think about trying to squish a rock. It's not going to happen, right? So, in a nutshell, that's what make solid a solid. It's all about how the particles are arranged and how they can move. So, solids are actually pretty amazing. Now, let's move on to liquids. Imagine you're pouring a glass of water. You see how the water takes the shape of the glass, and that's one of the key characteristics of liquids. Unlike solids, liquids don't have a fixed shape. Instead, liquids liquids mold to fit their container. But just like solids, liquids do have a fixed volume. So this means that they always take up the same amount of space. Now let's think about the tiny particles that make up the water. In a liquid, these particles are close together, but we should take note that their particles are not as close as in a solid. And here's the cool part, particles of liquids can move around freely. This is why liquids can flow and take the shape of their container. And just like solids, liquids have also a definite mass. So this means if you were to weigh the glass of water, it would always weigh the same. Okay? So that's the lowdown on liquids. They're free flowing, they take the shape of their container, but they always take the same amount of space. Now, how about gases? As we know, when we blow up a balloon and it just keeps expanding until we stop blowing, that's because the air that we're blowing into the balloon is a gas. So gases are also pretty unique compared to solids and liquids. So gases don't have a fixed volume or shape. Instead, they completely fill their container. Now let us think about the tiny particles that make up that air. So, in a gas, these particles are far apart and they can move freely. They rarely touch each other. And this is why gases can expand and fill up any available space. And here's another cool fact about gases, they can mix rapidly into any atmosphere in which they are released. That is why, for example, if someone sprays perfume or cologne in one part of the room, you can smell it all the way on the other side of the room. So that's the scoop on gases. They are always on the move, filling the space and mixing with the atmosphere. And how about the fourth phase of matter, which is plasma? Now, plasma might sound like something straight out of a science fiction movie, but it's actually the most common state of matter in the universe. I know it's crazy, right? But plasma is actually a little bit like a gas. But the particles in plasma are electrically charged. This happens when a gas gets really hot or is under a lot of pressure, and the atom starts to break apart into ions and free electrons. But despite all this, plasma has no overall electric charge. It's a bit like a crowd at a concert. There's a lot of movement and a lot of energy, but everyone's just doing their own thing. So you can find plasma in a lot of places. For example, the beautiful colors of the aurora, or sometimes we call them aurora borealis or the northern lights. These are caused by plasma in the Earth's atmosphere. And you know those neon signs or neon lights that light up during the night? Those are filled with plasma too. So even the huge fireball created by a nuclear explosion is a form of plasma. So that's plasma for us. It's wild, it's energetic, and it's all around us from the neon lights in our cities to the forest and until it reaches the universe. Okay, now I want you to look at this image. So, when you leave a glass of water in the freezer, it turns into ice. Or how when you boil that water, it turns into steam. These are examples of matter changing from one state to another. And this happens because of energy. Now, let's discuss this one by one: melting, evaporation, and ionization. How does these things happen? So, let's talk about melting first. When you add energy like heat to a solid, it can turn into a liquid. So, as what you can see in the image, this is what's happening when ice melts into water. Okay? Now, how about evaporation? If you add even more energy, or let's say more heat, to that liquid, it can become into a gas. Now, that is what's happening when water boils and turns into steam. And we call the process evaporation. Now, how about ionization? So, if you add a whole lot of energy or heat to a gas, it can become plasma. That is what's happening in the sun and other stars. They're so hot that the gases they're made of have turned into plasma. But it's not just about adding energy. You can also take energy away. For example, if you cool down steam, it condenses into water in the process called condensation. And if you cool down water, it freezes into ice. And that's the process we call freezing. So whether it's a solid, liquid, gas, or plasma, it's all about adding energy. So add energy and we can change into a solid into a liquid into a gas, or a gas into a plasma. So please remember these terms: melting, evaporation, and ionization. So from solid converted into liquid, from liquid converted into gas, and gas converted into plasma. And why is that so? Because of energy. So more energy, then the phase of matter will also change. Okay? I hope you understand that. Now let's talk about physical changes. So, when you leave an ice cube out on the counter, it turns into a puddle of water or it melts. That's actually a physical change. Physical changes are all about matter changing form. But even though the form changes, the actual substance stays the same. So let us uh, talk about physical change and chemical composition as stated on the slide. Physical change happens when matter changes form but stays the same substance. So, when our ice cube melts, it goes from being a solid to a liquid, but it is still water. The molecules are just arranged differently. So, in a chemical composition of physical change, the chemical composition of the substance doesn't change. All right? So, this means that the atoms that make up the substance stay the same. They might move around a bit, but they don't break apart or form new atoms. So, whether it's an ice cube melting, or water boiling, or even a piece of paper being torn, these are all examples of physical changes. So, the form changes, but the substance stays the same. That's it for physical change. Now, how about chemical change? When we strike a match, it lights up and creates heat and light. So that's actually an example of chemical change. Chemical changes are all about substances changing into new substances. Now, chemical change will actually happen when a substance changes into a completely new substance. For example, when hydrogen gas reacts with oxygen gas, it converts or it can form into water molecules, and that's a chemical change. So we have here the term chemical reaction. In a chemical change, a chemical reaction happens, right? So this means that the atoms that make up the substance break apart and form new atoms. They rearrange to form new substances with new properties. So whether it's match lighting, iron rusting, or even a cake baking, these are all examples of chemical changes. The substance changes and something new is formed, and that is chemical change. Now, let's talk about the difference between physical and chemical changes. Physical changes is what we have discussed earlier are all about changing the form of a substance without making a new substance. It's like when we melt an ice cube. The ice cube turns into water, but it's still H2O, right? It's just changed from solid to a liquid. Other examples of chemical changes include boiling of water, shredding paper, or chopping of vegetables. In all these cases, we're changing the form of the substance, but not the substance itself. Now, how about chemical change? Chemical changes are a whole different. So we're actually making a new substance. So let's think about when we light a match. The match burns and creates smoke and ash. Those are new substances that weren't there before. Other examples of chemical changes include combustion, like burning of wood, rusting iron, digestion in our bodies, or even a banana rotting. In all these cases, new substances will be or are being formed. So, whether it's a physical change or chemical change, it's all about what's happening to the substance. So, the question is it changing? Is it changing form but staying the same substance? So, if your answer is yes, then that's a physical change. Now, another question is it forming a new substance? If your answer is yes, then that's a chemical change. Okay, moving on. Let's have the differentiation between physical properties and chemical properties. So we have two main categories, right? So physical properties are those that we can observe and measure without changing the chemical identity of the sample. So, for example, we have color. This is probably the most obvious one. It's what allows us to distinguish between a red apple and a green apple. So, color is an example of physical properties. Length, this is a measure of how long something is. For example, a pencil might be 15 centimeters long. Now, volume, this is the amount of space that holds, or this is the amount of space that matter occupies. For example, a bottle might hold 500 milliliters of water. And we have opacity. This is the degree to which light can pass through matter. For example, glass is transparent, but wood is opaque. Now let's talk about chemical properties. Chemical properties are observed and measured as the sample changes its chemical identity. So they're like the inner nature of matter. So we have the terms acidity, reactivity, flammability, and toxicity. Acidity is actually the measure of how acidic a substance is. Say, for example, lemon juice is acidic, while baking soda is basic. And in terms of reactivity, this is a measure of how readily a substance undergoes a chemical reaction. For example, sodium is highly reactive, while gold is not reactive or not highly reactive. And then we have flammability. This is a measure of how easily a substance can catch fire. For example, gasoline is highly flammable, while water is not flammable. And lastly, we have toxicity. This is actually a measure of how harmful a substance can be to living organisms. For example, snake venom is highly toxic, while water, of course, is not toxic. So, whether we're looking at a rock or a glass of water or a puff of smoke, we can use these properties to describe and understand the matter around us. Okay, so here are some additional information. Again, physical properties or characteristics that we can observe with our senses or measure directly without changing the substance chemical identity. And other examples include odor. So when you say odor, this refers to the smell of a substance. For example, vinegar has a strong and sour odor. We also have texture. In terms of texture, it refers to how a substance feels. For example, the sand is gritty, while the silk is smooth. So that is all about texture. And we have hardness. So how resistant a substance is to being scratched or dented. For example, diamond is very hard, while clay is soft. And we have luster. This refers to how a substance reflects light. For example, gold has a shiny luster, while chalk is dull or not shiny. And we also have sound. So this refers to noise a substance can make when struck. For example, a bell makes a ringing sound. And then physical properties also include state at room temperature or phase at room temperature. So whether a substance is solid, liquid, or gas at room temperature, for example, water is liquid at room temperature, or a gas in a room temperature, or a solid in a room temperature. And then we also have the numerical descriptions such as density, melting or freezing point, and boiling point. These are numerical descriptions that, of course, requires measurement. For example, water boils at 100 degrees Celsius. Of course, we would need a thermometer to measure it. How about chemical properties? So again, chemical properties describe how a substance reacts with other substances. And this includes reactivity and flammability is what we have mentioned earlier. For example, reactivity, again, this refers to how readily a substance undergoes a chemical reaction. For example, potassium is highly reactive. And flammability, again, this refers to how easily a substance catches fire. For example, gasoline is highly flammable. And then we also have interaction with water. So whether a substance dissolves, rusts, or reacts with water. So, for example, salt dissolves with water, iron rusts in water, and sodium reacts violently with water. And we also have interactions with acids. So, whether a substance reacts with acids, for example, marble reacts with hydrochloric acid to produce carbon dioxide gas. So, this is corrosive, right? Now I want you to look at this image. So properties of matter are actually divided into two main categories, the chemical property and physical properties. So these are just additional information. Again, when we say chemical property, it is a property that becomes evident during a chemical reaction, for example, flammable or reactive. But in the case of physical properties, right? So it is a property that can be measured or observed without changing the chemical composition of the substance. And furthermore, we have two types of physical properties. It could be an extensive physical property or an intensive physical properties. When we say extensive physical property, it cannot be used to help identify a substance because it changes, for example, mass or volume. So these extensive properties could change, okay? While intensive properties, on the other hand, this can be used to help identify a substance because it does not change with the amount of matter present, for example, color or the melting point. Okay, so these are examples of intensive and extensive physical properties. Now, look at this another image. We have properties of matter, and here is question: are these properties determined without changing the identity of the substance? If your answer is no, then it is classified as a chemical property. Now, another example, how does a substance reaction to the presence of air, acid, base, water, or other chemicals? Now, on the other hand, if your answer is yes, then it could it could refer to physical properties. Now, another question we have here, does the properties depend on amount of substance? If your answer is no, then you are referring to intensive physical properties, and this include color, melting point, boiling point, and density. Now, if your answer is yes, then you are referring to extensive physical properties, and this includes mass, volume, length, and shape. Now we have here difference between intensive physical properties and extensive physical properties. So just an additional information. Intensive properties are physical properties that do not depend on the amount of matter. On the other hand, extensive properties depend on the amount of matter. Okay, and then some examples include melting point, boiling point, density. Under extensive properties, some examples include volume, mass, and energy. Okay, so I think it's just talking to the same thing, but in a form of Venn diagram. So just please read this by yourselves. All right, so let's practice. Identify whether the following is a chemical or physical change. Mixing of candies. Wait, what do you think? Chemical change or physical change? So the answer is physical change. So look at these candies. So you're just going to mix them probably in a bowl, right? So there's no actual chemical reaction going on. So it's just physical change. So identify whether the following is chemical or physical change, cooking an egg. So cooking an egg. I will not give you the answers, but I want you to identify by yourselves later. How about banana rotting? This chemical change or physical change? How about breaking an egg? Is this chemical change or physical change? How about dry ice sublimation? Is this chemical change or physical change? How about baking a cake? Chemical change or physical change? And now, breaking a glass. Chemical change or physical change? Folding paper. Is this chemical change or physical change? How about vinegar plus baking soda? Is this chemical change or physical change? Metabolism. Is this chemical change or physical change? And how about photosynthesis? Chemical change or physical change? Then we also have fermentation. Is this chemical change or physical change? Cutting of hair. Is this chemical change or physical change? And how about fireworks? Is this chemical change or physical change? And chopping of wood. Is this chemical or physical change? How about iron rusting? Is this chemical change or physical change? Now we have bleaching or coloring of hair. Is this chemical or physical change? Now burning of wood. Is this chemical change or physical change? So that's it. Thanks so much for watching and listening. And please, students, I hope you will really watch the lecture and listen to the lecture and prepare for a summative exam next week. See you again next week. Bye.